So finally, we arrived at the last lecture, which is the generative model, second part. So in the previous lecture, we have shown this taxonomy of generative models. And in lecture 19, we have covered this pixel CNN and pixel RNN and variation autoencoders. And today, we're going to look at generative adversarial networks, or GAN for short. And this will be the very last topic we're covering in this course. So, GANs. Let me just first show the current state of the art of GANs. So this was the very first model in 2014 that, wow, we can generate some fake human face. It looks real. And in the next year, wow, we can actually generate some color image, and it's even better than previous year. And every year they improve the performance of GANs really, really quickly to generate like really real-like images these days. And this one is actually interesting to see. So I'm not sure if you can see this. Yeah, because of this ads, it's really hard to show. Let me try to just log in. So yeah, you can actually try to look at this using the slides. So let me just scroll it down, and you are going to see how this face are going to changing. Let's see. You see the slide changes when I just scroll it down. The face slightly changes when I just scroll down from a lady to a man. And that guy becomes older, and hair changes. And now he has the glass. And he became a lady again, which is different. So yeah, this kind of technology is now possible. So we can learn some embedding space which governs the shape of this face, human face, in a variety of vectors. And yeah, they can even make this kind of applications. So this is from 2020, November, exactly 1 year ago. So using StyleGAN and recent models, we can actually create some fake photos like this, which is amazing. Just from 6 years ago, we were just able to creating this small image, but now we can create this realistic images in that, like this we've seen in this example. So this is based on the technology called GAN, and we're going to learn its basic ideas and what we need to consider in practice. This is another example that a GAN algorithm generated this image, and the developer of this model actually sold this image on online auction, and this one was like sold for $432,000, or in Korean it's like 5억 won. Wow, you just develop some GAN algorithm and you earn this money. Isn't it cool? So yeah, that is a good motivation for you to study GANs. So here's the description of GAN. Our goal is generating, building some model which generates realistic images. And we have some image collections, and we want to teach the model to learn about the distribution of those images. And once it's trained, then we hope the model is able to generate some realistic images, which as if it's a part of this data set, but it's not a repetition of the existing ones. So in GANs, we don't model the PZ, like the variation autoencoder, but we use additional network called discriminator. So in the real data set, we call the X for the real data sets. We have some images like that. So we sometimes give these real images to the discriminator, and sometimes we generate, using this generator, from some normal distribution, our some embedding, we generate some image and we give it. And the discriminator doesn't know which one is coming from, and it tries to discriminate. It's either it's from the real image or it's from the fake image. And the goal of this discriminator is for the real image, it wants to say it's real. For the fake image, it wants to say it's fake. The goal of this generator is fooling this discriminator. It tries to generate some realistic image as much as possible, and its goal is making the discriminators say that that's real, even if it's fake. So that's just this is the entire structure. We don't have to work on all the mathematical formulas as we've done in VAE. Here, we just build some neural networks and just leave it to learn between these two. So let's see. The discriminator part. So suppose we have some generator, and from the perspective of this discriminator, the loss function looks like this. So input is a real image in the training data or a fake image generated by the generator. So we don't know, the discriminator doesn't know which one is coming from, and its task is distinguishing whether that's a real versus fake. So it outputs the probability that the input is actually a real image. So if it believes it's a real image, it will output close to 1. And if it believes it's a fake-like image, then it will output close to 0 using the sigmoid. OK, then let's see. This left part is the discriminator. Given the real example, x, we want to have high output on this. So it wants to maximize this formula. And here, for the real images in the data set, the discriminator outputs larger values or close to 1. The score is between 0 and 1 because we are using the sigmoid. So maximizing this means that this part becomes 1, close to 1. And for the other part here, the discriminator gets this, which is given some random vector, the generator creates some image like this. It might be random-like or real-like this. We don't know yet, but it outputs some image, and the discriminator takes that. But the goal of the discriminator is figuring out that's fake. So for this one, we want to output 0 because it's coming from the generator part, even though it looks really real. OK? So that is the goal of the discriminator. And the discriminator wants to maximize this score. Remember this. We're going to see the opposite in the generator side. In the generator, it just receives a random vector, just like the VA. So getting some random vector from the the normal distribution. It generates some image. We don't talk about how we are going to make this generator yet. We're going to see later. And it outputs some real-like image. Its goal is outputting it should be a real-like image, which we can fool the discriminator. So the objective of this generator is, it's the same formula like this. The second term of this formula, the same thing. But the generator wants to output some image such that the discriminator believes it's true. So it outputs close to 1 or larger values. So when G generates an image, its goal is to increase the P of real such that this becomes to close to 1. So this entire part will becomes 1. That means this 1 minus that is becoming to 0. So its goal is actually minimizing this as much as possible. So that is the game between the generator and the discriminator. Discriminator wants to maximize these numbers, and generator wants to minimize these scores. So they fight to each other. So the generator learns to generate more real-like images, and at the beginning, it will be more like random. And from the discriminator's perspective, it's easier to distinguish between the real and the fake images. But later, the generator gets improved, and then it's getting harder and harder. And then at some point, we are going to see that the generator is actually creating some real-like images. When we train the generator, we don't deal with the real examples. So it's nothing to do with this here. So combining these two formula, we can actually write like this. So these two are what we've seen in the previous slides. This is the objective function for the discriminator, and this is for the generator. So generator wants to maximize this formula, or this, and the discriminator wants to maximize this by optimizing its own parameter, theta d, while the generator wants to minimize this as much as possible by optimizing its theta g, right? So even though where both of them will be improved from this fighting, and then even though the overall loss might not significantly decreasing like other machine learning models, but still both of them are improving from this fighting. So we were going to see some improvements on the actual examples they are generating. So here, this discriminator wants to maximize, so it uses gradient ascent, not gradient descent, because it's maximizing. Or from the generator side, it uses the gradient descent to minimize this as much as possible. And this is the algorithm of applying these ideas. It's actually exactly the same. It looks complex, but let me show you. Just ignore this part. For case steps, they initially proposed to repeat this part multiple times, but actually they used k is equal to 1. So you can actually ignore this part. So in this part, the first half, they sample m fake examples, which is called z, where z is just random vector. And from there, it generates some fake images, m fake images. And they take m real images, x, and then update the discriminator based on this. So they have the same number of real images and the fake images, and it trains the discriminator with the fixed generator to better distinguish these real and fake examples. And then we generate another m fake images, and at this time we just update the generator only to minimize this loss function. And we just repeat. So one is fixed and the other is updated, and that is fixed and the other one is updated. And we just repeat alternatively like that. Then we're going to have better generator in the end. So the idea sounds really simple, but actually implementing this has a lot of practical issues. So let's see the first one. So as you imagine, at the beginning, generator will do nothing, right? It doesn't see any examples yet. So we cannot generate any real-like images at the beginning. So generator will be just full at the beginning. And then if the generator draws something really poorly, then what about from the discriminator's perspective? It's too easy, right? Discriminator can distinguish the real image versus fake one really, really easily at the beginning, which means for those fake images, the probability will be almost 0, very close to 0. And that means this is the discriminator's output. So if that is close to 0, this blue curve draws this log 1 minus x. So if the input is close to 1, which means the generated image is more like real, the gradient is larger. But if it's more like fake and it's too easy, then the gradient becomes close to 0 or gets smaller, as you can see in this image, right? So gradient with low d value is relatively flat. And that means this gradient is the, and also the important fact is that because the generator can be trained only through the discriminator signal, remember this structure, the only gradient we can receive in this model is through this one. We don't have any other path to give the actual ground truth. That is the only signal. So it needs to go through this discriminator first to have these gradients get updated. So this is a serious problem. The gradient is only coming from the discriminator. So the generator at the beginning is suffering from vanishing gradient problem because this close to zero value will be multiplied and the gradient will be vanishing, which was a common problem when we discussed in lecture 8 or 7. So what's the solution? So they have devised quite smart idea. Instead of minimizing this, here they wanted to minimize this part, which means they want to maximize only this part, right? DGZ, if this part is maximized, then the entire this formula will be minimized. So why don't we just do that? The idea is like that. So 1 minus d is changed to just d, and instead of minimizing that, they want to maximize that. And then the curve will look like this, the green one. So when the discriminator works poorly at the beginning, the gradient is much larger. And once it's trained, then the gradient will get smaller, which is okay or even ideal, right? So yeah, that's just a high-level idea. And if you are interested in the details of these things, please see this tutorial linked in the slides for more details how they do this. So this is actually one more thing we have to talk about. So what model we are going to use for the G and D? We have to make them, right? So in the original GAN paper, interestingly, they tried actually two things. One is just fully connected. So given some vector Z, they applied they just stacked some fully connected layers to map it to real image. And then for the discriminator, they just use the fully connected layers to figure out or to discover the stuff in there to and decide if that's a fake or real. And they also tried some deconvolution and convolutional combination for this small data set. But yeah, that's why this model was actually poor like this. So anyway, so these are the fully connected model trained on CFAR10, a small data set. And these 5 are the generated image from their GAN model. And this one was the yellow one is the closest training example observed in the data set. So which means this one explains that these 5 images are where it kind of intended a horse, but we don't see that it's, well, actually that's very different from horse in my opinion. Where this one is a puppy, but with all of these we cannot see that it's like a puppy. But still, these images, this is the very first GAN paper, and we see that these are still somewhat look like a real image, not just like random distribution of the pixels. So after this paper, a lot of people tried to improve the quality of those images. And the first one was this one, deep convolutional GAN. So that's quite obvious, right? Why don't we just use the convolution instead of the fully connected? So they applied convolutions, and yeah, also the vanilla GAN had other problems as well. So it's too unstable to train because it's just 2 different modules in the model are fighting to each other. So it's different from our other machine learning models that if we look at the loss curve, we see that, wow, this model is learning something, or this is overfit, or this is not doing anything useful. We can do that by looking at the loss function and the loss curve. But this one is not. They just fight to each other, and the quality of each module is improved at the same time. So it looks like the loss is not decreasing very quickly, but still they are improved. So it's really hard to train them, and it's really unstable at the beginning, especially. And also, it's a black box method, so we are not able to explain why or how they actually generate those images. We're going to apply some other recent techniques to provide some explanations, especially using some models like GAN in the, probably in the on Wednesday. So another question people arised was like this: how should we evaluate the quality of those models? Well, first of all, it's too subjective. We just look at those images and wow, this is real-like. But if we want to improve that a little bit more, then how can we compare them? And also, we were not actually able to answer to this question. Are these really generating some new images, or just slightly modify some images already in the data set? So it's really hard to say, because we have to compare all the generated images, and if there are similar ones already in the data set, it's not possible. So in the DCGAN, they applied some modifications like this. All of them are more like engineering stuff. Like they replaced all the pooling layers with trident convolutions and deconvolutions. We mentioned that we actually mentioned this in lecture 8. In GANS, we don't use pooling layers, and that's actually coming from here. So instead of a pooling layers, which is a deterministic function, we apply the convolution and deconvolution to increase or decrease the feature size, and it learns how to do that from the data, not by average pooling or max pooling, which is a deterministic functions. And they applied batch norm and removed fully connected. All of these are the common things these days, but this paper was kind of the first one who applied these things in the GAN model. So I just summarized it here. So yeah, it's their architecture. So starting from some random vector, it applies 4 times of 5 by 5 deconvolution layers, which we learned in image segmentation lecture in lecture 10. And then the discriminator needs to classify if this is a real or fake. So it applies 5 by 5 convolution layers with stride 2 to reduce the size until this 4 by 4 features. And then it decides if it's real or fake based on those features. So when we generate, we need to upsample. So they use deconvolution. And when we recognize something on the image or distinguish if that's real or not, we apply the regular convolution layers to classify them. So it's kind of common architectures. So again, we don't have to do all the mathematical things when we design the generator. We just use this deconvolution layers stacked, and then boom, it just outputs some realistic images. And in their paper, they actually provided these interesting examples, which provides the interpretability of these vectors. So you probably remember that we've actually seen very similar thing using the word vectors in natural language processing. So given these 3 random vectors, which are close to each other, from this, this model generated this image, and this image. We know that all of these are men, and they wear glasses. And they also generated another images from other Z's, where they generate the man, but without glasses. So just take the average of these 3, and then it gives like this. And take the average of these 3, then it generated this image. And so so we take the subtraction from this one, we subtract this. That means man with glasses minus man without glasses. And then we add women without glass. Then what we would like to expect? Women without glass, with glasses, right? We just remove the components of without glass from this one. and then add women. So then what we would like to have is the women with glasses. So this one was possible with these embeddings, and they argued that they kind of provided interpretability of the vectors, which is interesting to see. And another interpretability experiment was like this. From some bedroom data set like this, they try to generate some images, and they are shown in the leftmost and the rightmost. So those yellow boxed images are actually generated from this model. And we know that these are coming from some z vector in the latent space, right? So we take those two vectors, and then we can connect them in the latent space by a line, and then we can gradually move through that line to just gradually change the z vectors from one to another. And then using those intermediate vectors on that line, we also they also tried to generate the images, and they wanted to see that that's actually generating some image in the between these two. And this one is actually showing that. So between this image and this image, on the points connecting those two latent vectors, those latent vectors actually generated images like this, gradually changing this room to this room. Quite interesting, right? So you can actually see more examples in this paper. So yeah, these two models are the oldest, the most fundamental GAN paper. And we're going to see some of its limitations and how we can fix them. So limitations of this GAN model is, we mentioned the unstable training. So like this. So the GAN objective is defined as how well the discriminator distinguishes real versus fake, right? This one, not based on the quality of the generated images. Because of this, even though we draw the loss or the objective function, even though it looks getting better, they actually just look like just stay the same. It's not getting better. But if we actually see the generated images by each of those intermediate models, we see that it's actually getting better. So the objective function doesn't indicate the quality of the outputs in this model. So how can we fix this? It's hard to tell if the generator is actually well trained or not, just from this loss. And yeah, here are some also mathematical stuff, but I'm not going to go to the details here. But mathematically, it can be shown that minimizing the GAN objective, which is this, with an optimal discriminator is equivalent to minimizing the JS divergence. And JS divergence is defined as this, which is the KL divergence. Recall that the KL divergence is not symmetric, right? KL divergence from P to Q is different from Q to P. So to use this as a kind of symmetric distribution, they designed like JS divergence like this. So half of this P2 average of them and Q2 average of them, and they just take the average of them. So it's just KL divergence, basically. So when we draw the KL divergence or JS divergence figure like this, then we see that if the two distributions are very different, then the gradient will be close to 0. So here, the x-axis is the mean of the Q. And if they are very different, the value is very large, then we don't see any gradients here. So the gradient will be close to 0. And they argue that this one is actually causing another diminishing the gradient problem, and it causes the unstable training again. So this is what you need to just remember. when the generator does not work well at the initial stage, it learns almost nothing from the discriminator signal. And that's intuitively, that sounds correct, because at the beginning, we know that discriminating a real-life image and the fake image is really easy at the beginning, but generating some real-life image is much harder task. And suppose you are a kid who have never drawn any figure, and your art teacher just lets you to draw something, and she just says that, okay, that's not image, that's not a picture, that's not a picture. And then are you going to learn how to draw a real-like picture? It's really hard, even for human. So they are talking about this kind of phenomenon, especially when we are using this JL divergence. And this is another really important problem of the original GANs, which is called mode collapse. So what was the goal of the GAN? We wanted to generate real-like images, which is able to fool the discriminator. That is the original goal, right? So from this generator side, it can actually cheat. So for example, it is given all the 10 digits in the data set, but it just, okay, 1 is the easiest one, and 7 is the next easiest one. So it just forget about that, and it just draw 1 always. And then the teacher says, okay, that's a digit, that's a digit. So it will get some credits from that. So it forgets about other numbers, but it's still able to generate all of these images, which look real, right? So it's the grading criteria for them. So, okay, this is, I draw this, and the teacher says that, okay, that's a real digit. Okay, good job, again and again. But it never tries to draw like 3 or 4 or 7, 8 or 9, which is more complex. That is called mode collapse. In the data set, we have much more complex stuff existed, but the generator just forget about them because that's too hard for me. And it just produces samples lying on a few modes. So in this kind of data set, it's easy. We know that it's not outputting all the possible digits. But what about ImageNet? If we train a GAN model on ImageNets, then can we decide if this model is well trained to output actually reflecting the distribution of all the classes in the data set? That might be possible for ImageNet because it's labeled, even if it's large. But what about just random collection of images on Google? It's hard, right? We don't know whether that model forgot some important stuff or not. So this model collapse is a really problem in GANs. And this Wasserstein GAN proposed a solution to that. So instead of KL divergence, they actually try to use another distance called Earth mover. And again, I will omit all the complex math here and just give you the conclusion, which is super simple, surprisingly simple. They changed their objective function to this. Looks very similar to what we've seen before, right? What was it look like before? It was like this. So in the original GAN, it outputs, it gets the real image from X or fake image from Z here. And then the discriminator was trained by this, right? It wanted to maximize this score as much as possible and minimize this score as much as possible. They just removed this log stuff here, right? Still, they would like to maximize the score for the real examples and minimize the score for the fake examples, but they just removed this sigmoid function. So the score doesn't necessarily between 0 and 1 now. It can be arbitrarily large values or arbitrarily small values, which means the negatively large values. And the generator is the same. In the GAN, they wanted to have increase this value as much as possible to fool the discriminator. It's the same here. Generator wants to produce real-like images to fool or get a larger score by this discriminator. They changed the name to critic because it's not discrimination based on 0 to 1. So they just changed the name to critic, but it's basically the same thing. So in the previous slides, I summarized that this FW, what they call critic, now gives any arbitrary real number and tries to make it as large as possible for the real values, real images, and as small as possible for the fake images. That's the role of the critic. It's the same as the discriminator in the original GAN, just the range is extended to -infinity to +infinity. Okay, but I omit the mathematical details, but actually during that derivation, only one additional condition exists, which is because of the mathematical condition with this EM distance, this FW needs to satisfy some condition called one Lipschitz continuous. If you are from mathematics background, you maybe know what it is, but you don't have to here. This is just the conclusion. The weight W needs to be small. And the way they actually tried was if it's larger than C, some constant C, then just clip it. So the weights are just forced to stay between -C to C by clipping. That's what they have done with the Wasserstein GAN. So here's their results. Using the GAN, we knew that its objective function doesn't say anything. Even though it's staying the same, still we observe that the quality gets better. In this WGAN, the loss function is reduced like this, as what we've seen in other machine learning models. And the quality also gets better according to the loss function, which is ideal. And according to the paper, they argued that they solved the model collapsing problem without any interesting experiments. So I don't know. They just argued that. But yeah, who knows? Okay, so Wasserstein GAN solved these problems, hopefully, but it has also its limitation, which is related to that clipping part. They just force the model to stay to have some limited range from -C to C by clipping those values once it's larger than that, which sounds unreasonable or not ideal, right? So that was actually causing the problem. The model needs to specify this C as a hyperparameter, but it was too sensitive to that. So if we set it to too small, then the vanishing gradient happened. And if it's too large, then the gradients exploded. It was too hard to find the correct or right values of C because we don't know what the weight values will be once we train the model. So this model called Wasserstein GAN with gradient penalty, or WGAN GP, applies actually really simple idea to solve that problem. So instead of clipping, they just added some additional gradient penalty term that the gradient needs to stay around 1. And if we set this lambda large, then it's forcing more to these gradients needs to be close to 1. So instead of just hard clipping, they just applied soft regularization penalty to achieve the same effect. And actually, by that, this gradient penalty, the gradient norm was staying around 0. So it was able to train the model much more robustly. So here's the results. WGAN with clipping, you see that these creepy images. And using this WGAN GP, we see that these images are much more cleaner and more realistic, and yeah. So okay, I think we can stop here because let's see, we have 10 minutes left. Okay, yeah, let's just start a little bit. We have too many things left if you stop here. So yeah, let's just do a few more slides. So far, we learned the basics of the GAN. To summarize it, the GAN model tries to generate some realistic images from resembling the distribution of the training data set. And it has some practical issues, so a lot of people try to add some ideas to make it more robust, and also try to solve some problems like the mode collapse. So that's the first chapter of this lecture. And from now on, we are going to see another task, which is image-to-image translation. So image translation is a task of transforming images from one domain to have the style or characteristic of the images from the other domain, maintaining their semantics. So here are some examples. Suppose you have one domain like this, the area map, and the other is actual map. So we know that as a human, these two types of images has one-to-one correspondence. We expect once we locate some area, and if we click the area map there, we would like to see exactly that area of the Earth using in this kind of style, the area map. And the roads needs to be exactly matching to each other, so something like that. Or something like this, day to night. It's exactly the same place using the same camera, but one is from the daytime, and the other is from the nighttime. Or it can be one is from spring and the other is from winter, or something like that. Or even this kind of thing is also possible. The drawing of some back and the actual back photo. So suppose just you have two different domains describing something in common, and they have one-to-one correspondence, and we'd like to transform one to another. So the first paper we are going to discuss is called pix to pix, or pixel to pixel. So here's the problem setting. A training example contains a pair of images. Now, the training example is a pair, not a single image, X and Y. And each of those are coming from different domain. And our goal is transform from domain X to domain Y, like this. This is the X domain, and this is the Y domain, the rear shoes. So the idea is the generator translates the image X to the style of the domain Y to fool the discriminator. So given this X image, we go through the generator to transform it to image looks like Y domain. And this discriminator gets either from the X domain image or Y domain image. And if that's real Y image like this, we want to train this discriminator to output 1 or real. And if it's coming from the X-like image, then it says it's fake or 0. But the generator will try to fool the discriminator by drawing real-like image from this X domain image or the sketch here. And if it really looks like a real, like here, then the discriminator will be fooled. So then this G actually maps the image in the domain X to domain Y. So we are using the same idea as GAN to apply this paired data. Okay? So this is their objective function. Looks complex, but actually that's same as the GAN. So let's see. So discriminator is given both X and Y. And it tries to maximize this output if X is coming from the X domain and Y is coming from actual Y domain, the real paired data set. No generator participates in this. So if it's a real pair, the discriminator wants to output 1, right? That's the goal. This part, if the real Y is not used, but we use the generator to fool or generate Y domain image from X, then the discriminator needs to output 0. So discriminator wants to maximize these two terms by figuring out if it's a real exemplar or it's a fake exemplar. So this red part is associated with the discriminator. And the generator, same as before, it tries to fool by generating more like Y domain images given X, the sketch of the shoes. It wants to generate actual shoes-like image, but it's not from actual Y domain. It just tries to fool the discriminator. So G tries to minimize this by fooling D to assign high score for this part. Same as before, just the input is the two pair of images. And we have the last term. So G tries to minimize this by creating an image as similar as the ground truth pair. So because we have the ground truth pair image of this Y, the real Y image, the real shoes image, we can actually compare pixel to pixel between this real image and the generated image from the sketch, the X. So we add this as a reconstruction loss. So the first part, the two terms are same as GAN, just adversarial loss. And the second part is actually the reconstruction loss, which we help the generator to generate real-like images. And not just real-like here. Why do we need this part? If we don't have this part, it can just generate any shoes image. It doesn't necessarily match to the sketch of them. It just outputs some image, real-like image, and just memorize that and always output the same image. But still, the discriminator will, okay, this is like the real image in this domain. But with this loss, actually, we can force the generator to actually follow the semantics of the input in the X. Okay, so their implementation details, they used UNet, and they proposed the patch GAN, which is the discriminator. Now, they don't, with this patch GAN, they decide real versus fake based on each patch, n by n patch. So if it's 1 by 1, then the entire image is determined is either real versus fake as the previous GAN. But if they use, for example, 16 by 16, then they use 16 by 16 image patches to figure out that's real versus fake. And then they can learn more fine-grained image generation quality using this. So that was one of the small ideas. And here are some examples. There are a lot of interesting ideas where here are the area photos on Google Maps. Either way, you can actually generate this area photo map from just just map. So given this, it can generate like this. From this to this sounds easy, right? But from this to this one is much more difficult. We have to draw more like photo-like images. And some other interesting examples like this, just draw some pictures like that, and it just tries to fit some animal inside the this bread. Or it is also applied to background remover, or from sketch to portrait, or many other interesting things can be possible. And there are even apps actually you can download and try these things. So here's the summary. Their contribution is photorealistic image-to-image mapping is achieved for the first time. And that was possible because of these GAN-based models. And they proposed the patch GAN, as I mentioned. And this is applicable to various image-to-image translation tasks listed here. And the limitations are this. The biggest limitation of this approach is that they require paired images for training. So this is really serious limitation. In some cases like this, we have the Google map all over the world. So we can easily get the paired images like the map and the area photos. But some cases, it's really hard to collect the paired images. For example, we'd like to give the photo, real photo, and want to have some pictures styled like from Monet, or the opposite. given the Monet's picture, and we would like to actually get the real photo of that scene. This is not possible because we don't have Monet anymore in the world, and his artifacts is just a few numbers, and we don't have them that much pairs. So we're going to see other methods to overcome these limitations, which is cycle GAN and the disco GAN in the next lecture. So yeah, thanks for your attention. And if you have any questions, please stay and you can ask questions.